Okay, welcome one and all once again. So, in this lecture, I will discuss the efficient estimator. Okay, so once again, in this series, actually at present, I am discussing estimation, and here we are discussing the characteristics of a good estimator. So the first characteristic that we discussed, it was unbiased estimator. The second good characteristic was consistent estimator. Now the third characteristic for a good estimator, it is efficient estimator, means our estimator should be efficient. Now what is efficient estimator? What was its need? For that, consider this statement that sample mean X bar. This is an unbiased as well as consistent estimator of population mean. Okay, so this we have proved. Okay, in the previous lecture. Do watch that lecture if you want to know the details. Okay. Now, we have proved that the sample mean, it is unbiased and consistent estimate of population mean for any population. So if I am saying any population, that means the population, it may have normal distribution, it may have Bernoulli distribution or Poisson distribution or any another. Okay. So sample mean will always be unbiased and consistent estimator of population mean. What is this MD here? Actually, the sample median is also an unbiased and consistent estimator of population mean, but if your sample is from a normal population. Okay, so here, whatever you are seeing here means here this example, here our sample is from normal population. And what is this MD? MD is the sample median. Okay, so now expected value of sample median, it is mu. So from here, I can write expected value of sample median. It also tends to mu as n tends to infinity. Okay, I can write this thing. Okay, how it is so? Okay, actually, if you feel that some fact is not being explained properly, then please do watch the previous lectures. Okay, so almost each and every fact is well explained in the previous lectures. Now, variance of sample median, actually what is that? It is here, it is given pi sigma square by 2m, and also this is tending to 0 as n tends to infinity. Okay, so what's the meaning? That sample median, it is unbiased. Actually, what this equation proves, that expected value of sample median is equal to population mean. This equation proves that the sample median, it is also an it is an unbiased estimator of population mean. Just like uh, expected value of X bar, this is equal to mu. What does it prove? What does it tells us? It tells us that sample mean is unbiased estimator of population mean. Similarly, this equation, it tells us, it proves that, it means that this equation, it tells us, it proves that, it means that sample median is unbiased estimator of population mean. And the variance of sample mean, it is nothing but sigma square by n, which tends to 0. Okay, so this tends to 0 as n tends to infinity. So from here, expected value of X bar, it tends to mu. Okay, as n tends to infinity. Okay, both these. Okay, so this one and this one, they prove that sample mean is consistent estimator of population mean. Actually, I have discussed in previous lecture in detail. So here we have two estimators for the population mean, for the single unknown parameter. For this single unknown population parameter, we have two estimators. One is sample mean and another is sample median. And both are unbiased and consistent estimator of mu, this unknown population parameter. Now, a very natural question that which estimator is best or better means between sample mean and sample median. Okay, which estimator is better? For that, the concept of efficient estimator comes into the picture. Now, if of the two consistent estimators T1 and T2 for a certain parameter theta, if variance of T1 is less than variance of T2 for every sample size, if variance of T, wait, yeah, if variance of T1, it is less than variance of T2 for every sample size n, then we say T1 is more efficient than T2. Okay, just wait, please. Let me check it. So, if variance of T1 it is less than variance of T2, then T1 is more efficient than T2 for all uh, sample sizes. Now, uh, variance of sample mean it is sigma square by n. Okay, so this we can write that it is 1 time sigma square by n. So this is variance of x bar. And what is sample mean basically? Variance of sample mean. And what is variance of sample median? Actually, this is pi by 2. Okay, pi by 2 into sigma square by n. Actually, which is approximately equal to 1.57 times sigma square by n. So obviously this variance, the variance of x bar sample mean, it is less than this variance, the variance of sample median. Okay, so that's why we will say that sample mean, it is more efficient. Sample mean is more efficient, okay, as compared to sample median if our sample is from a normal population. Okay. Now, this concept of more efficient, it can be further extended to n plus 1 number of estimators. What I mean to say here means here in this example, we have only two estimators, okay, for the same parameter, and actually we may have more than two estimators also. Okay, so yeah, so suppose we have T1, T2 going on up to Tn, means n plus 1 number of estimators. Actually, T1 to Tn, how many estimators are there? N. And there is one more estimator, T. So total, how many estimators are there? N plus 1 number of estimators. You can see here. Okay. We will say T is most efficient among all these. So we have T, T1, T2, Tn, n plus 1 number of estimators for the same parameter gamma. And we will say T is most efficient among all these if variance of T is less than variance of Ti. Okay, for all I 1, 2, 3 up to n. If T has the least variance, T has the least variance among all these, then we will say T is the most efficient. So now we have a term called efficiency, EI. So what is this EI? It is the efficiency of TI. of the estimator TI. And actually this efficiency, it is a ratio, proportion, okay? So it is a ratio of the most efficient estimator, the ratio of the most efficient estimator to the estimator whose efficiency we are calculating. Okay, so EI, it is the efficiency of TI, and this is basically the ratio of the most efficient or with the least variance estimator. Okay, and this ratio is with the TI, variance of TI itself. Okay, and it is natural that this efficiency, it can never be greater than one. Why? Because this is the this one, it is this one, it is the definition of most efficient estimator. If you divide both side by variance of TI. Yes, variance of TI. So actually, since it can be itself, so it is a minimum. Minimum means it can be less than equal to. So now, what is this thing? Obviously, this is our EI. Okay, the efficiency of TI. And what is this thing? It is nothing but one. Okay, so EI, the efficiency, it is always less than equal to one. It can never be greater than one. Now, in our very first example, what is this E? It is the efficiency of sample median. Why? Because between sample mean and sample median, the sample mean was more efficient, or in a certain sense, most efficient if we are considering only two estimators, sample mean and sample median. So, the efficiency of sample median, it is the variance of most efficient divided by variance of the estimator itself, whose efficiency we are calculating. Sigma square by n, this is the variance of sample mean, and this is the variance of sample median. And if you divide, you obviously you will get 2 by pi, and which is nothing but this. And obviously, this is less than 1. Okay. Now here, actually, we have used the results that variance of sample median, it is pi sigma square by 2n, and expected value of sample median is also equal to mu. Okay, if our sample is from a normal population. Now these two results, they are proof. Once again, it is proof of these two. They are bit beyond the scope of present discussion. Okay. So here we have a sample. It is mentioned here that this is a random sample whose size is 5. It is drawn from a normal population. Okay. So with the unknown mean mu. Okay, one thing here, that if you are watching this video, please try to watch the previous videos starting from the first lecture. Otherwise, you may miss some understanding. Okay, or you may not be able to understand each and every word that is being explained here. So here we have a random sample of size 5 drawn from normal population whose mean mu is unknown. And since this mean mu is unknown, so obviously we will try to estimate this. Okay, now T1, T2, T3, these are the three estimators. Okay, these are the three estimators. Obviously to estimate what? Mu, because mu is unknown. Now, this lambda is such that T3 is an unbiased estimator of population mean. Okay. Okay. We have to find lambda so that T3 is an unbiased estimator of mu. So here are the options. Okay. Now, expected value of T3, it should be mu. Okay, so this is the basic definition of unbiased estimator, means the expected value of T3, it should be this. So now this is nothing but twice x1 plus this and by 3, okay, which is this, okay. And now 1 by 3, okay, sorry, 2 by 3 x this, okay, then 1 by yeah, so 1 by and this, and now this expected this, okay, that is nothing but this. Means here, or from here to here, I have applied the linearity of E. Okay, so now you can see 2 by 3, you can see this 2 by 3 into expectation of X. Okay, now what are these values? Actually, these are nothing but mu. Why? Because our very first result was that expected value of ith sample observation. The expected value of ith sample observation is mu. This I had proved. Okay. So here the symbols are capital X size. But if symbols are changed, that will not change the meaning of the uh, result. So 2 by 3 mu plus this thing. Okay. So all these means expectation x1, expectation x2, expectation x3, all will be nothing but mu because of this result. So uh, this is nothing but if you can cancel out, we can cancel out mu. So here it will be 1. Please mind, here it will be 1, not 0. Okay. So now 2 by 3 plus 1 by 3, it is obviously 1. And 1 plus lambda by 3 is 1. So this cancels. So now 0. This 3 goes this side. So what is lambda? The lambda is 0. Okay. So for lambda 0, our T3 will be unbiased estimator of population mean. Are T1, T2 unbiased? Only T1 is unbiased, only T2 is unbiased, or both are unbiased, or none is unbiased. So actually, expected value of T1. Okay, it will be nothing but 1 by 5 times expected value of x1, okay, plus 1 by 5 this, okay, going on 1 by 5 this. Actually, you have to repeat the same process. You can see this process. So obviously now what are these? These are all mu. So I think you know the answer will be nothing but mu. Means expected value of T1 will be mu. Okay, because mu 5 times. Okay, so T1, this is unbiased estimator of mu. Now expected value of T2. So I think you can calculate this. It will come out to be 1 by 2 mu plus 1 by 2 mu plus mu. And that is what? That is nothing but 2 mu. That is not equal to mu. Means T2 is not unbiased, rather it is biased estimator. Okay, so here only T1 is unbiased. Uh, State giving reasons, the estimator which is best among T1, T2, T3. Here best in what sense? Here best in what sense? In this sense that which one has least variance or which one is the most efficient. Okay. So either T1 is most efficient, T2 is most, or this one. Okay. So now, actually, if you have observed, you know what is our T1? T1, it is nothing but sample mean. The T1, it is sample mean. Okay. So actually, this is sum of all sample observations divided by number of sample observations. So that is sample mean. So we already know and we have already proved that the sample mean, the expected value of x bar, it is mu. So either you use this fact, okay, or you use that this one, okay. The final result will be that T1 is unbiased estimator of population mean. Wait, please. Now, variance of T1. Once again, what is T1? It is X bar, sample mean. And what is variance of sample mean? It is sigma square by n. And what is n here? It is 5, the sample size. Okay. So, this is equal to zero point 0.2 sigma square. Okay. Now, uh, variance of T1. This is actually variance of 1 by 5, actually 1 by 5 x1 plus here uh, this one. So this is now 1 by 25. Okay. I have applied this result that if x1, x2, x5, they are independent and they actually are independent sample observations, then variance of a1 x1 plus a2 x2 plus going on a5 x5, it is 1 by, it is A1 square. A1 square into various x1 plus A2 square into various x2 plus A5 square into variance of x5. Even this result I had discussed, used in previous videos. So now this is 1 by 25 sigma square. Because what is variance of ith sample observation? It is sigma square. Sigma square is population variance. Okay, so then 1 by 25 sigma square plus 1 by going on. Okay, so 1 by this, so sigma square by 5. Okay, so whether you use this fact that variance of the sample mean, it is sigma square by n, or you go by this way, the final is that this is sigma square by 5. Yeah. So variance of T2 now. So what is T2? It is x1 plus x2 divided by 2 plus x3. Okay. So this is now 1 by 4 variance of x1 plus this and plus this thing. Okay. So now it is 1 by 4 sigma square plus 1 by this and this. So what we are having? This plus this is 1 by 2 sigma square plus so 3 by this. And this is 1.5. 1.5 is so sigma square. Okay. So actually now do watch the previous lecture or even in this lecture how this is equal to this. Okay. Uh, variance of T3, then it is 2 by 3, 2x1 plus actually x2 divided by 3. Actually, lambda is 0. The lambda in T3 was 0. Please mind. Okay. So, here. Now, this is actually 4 by 9 and into sigma square. Variance of x1 plus 1 by 9 into, sorry, 1 by 9 into sigma square. And what is this sigma square? Variance of x2. Okay. And this is 5 by 9 sigma square. And this is actually roughly, it is 0.4, sorry, 9, it will be 5. So, yeah, point 5, okay, sigma square. Now, among T1, T2, T3, T1 is most efficient because it has the least variance. It has the least variance. Okay. And actually, once again, what is T1? Sample mean. So, mean sample mean. Okay. For normal population means if our sample is from normal population. So, even in this question, our sample is from normal population. So sample mean, it is a unbiased estimator, it is consistent estimator, even it is here in this example, it is the most efficient estimator also. Okay. So sample mean is one of the best estimators because it is having more number of good characteristics which are defined for a for an estimator. Now here there is a certain remark that important remark. Suppose in T2 instead of this plus it is minus. Then what changes will be there? Okay. So for that it is minus means x1 minus x2. So what will be uh, expected value of T2. So actually it will be now even here. Now it will be minus and obviously these two terms will cancel out and it will be mu. Means now even T2 will also be unbiased estimator of population mean, but in variance of T2 here. Yeah, here it is minus, but here it will not be minus. Here it will be plus. If it is expectation here, then yes, even here it will be minus. But if it is variance here, then here there will be no minus. Please mind. Why so? Because if you see here, what is your coefficient A2? Actually, what is your A2? It is minus 1 by 2. The A2. Actually, it is a variance of A1 x1 1 by 2 x1 plus minus 1 by 2 into x2 and plus x3. Wait, please. Okay. So, what is your this coefficient? It is minus 1 by 2. And what will be its scale? It will be still 1 by 4. Okay. So this is very important. Okay. Many times students commit the mistake that if it is minus, so even in case of variance, they write minus. No. Now the last thing that what is the efficiency of T2 and T3? Okay. So E2, it is variance of T1, the most variance of the most efficient divide by variance of T2. E3, this is variance of T1 divided by variance of T3. What is E2 and E3? The variance E2, it is variance of T2. E3, it is variance of T3. And in the numerator, what we have? The variance of the most efficient among T1, T2, T3. Now, this is easy job now. So what will be this? Variance of T1, it was sigma square by 5. And what was variance of T2? The variance of T2 is 5 by 9 sigma square. So here this sigma square cancels. Actually, this 9 will be in the numerator. This 5 will be in the denominator. So it will be 9 upon 25. And similarly, this is sigma square by 5. And what is variance of T? Oh, yeah, I have made a mistake. Actually, variance of T3, please mind. The variance of T3 is 5 by 9 sigma square. So, yeah, this will be 9 by 25. Actually, what is this E3? E3, it is the efficiency. E3 is the efficiency, okay, of T3. And E2, it is the efficiency of T2. So actually here it is 3 by 2 sigma square. Okay, so this sigma square cancels out. Okay, so this 2 will be here and this 5 will be here. So it will be 2 by 15. Okay, so obviously both the efficiencies are less than 1. So this E2, it is the efficiency of T2, E3, it is the efficiency of T3. And here in numerator we have variance of T1 and T1 is the most efficient or with the least variance. Okay, so thank you everyone.